Welcome back, calculus students. The topic for today is related rates. So related rates problems are a class of problem typically where there are several variables related to one another through an equation or maybe multiple equations, and each of the variables are changing over time. A classic example of this from physics is the so-called ideal gas law, PV equals nRT. In that formula, P is pressure, V is volume, T is temperature, and N has to do with how much substance is involved. So this formula relates the pressure of some sort of gas to the temperature and the volume of the vessel it's contained in, and how much of the gas there is. It could be the case that one or more of these variables is changing over time. For example, maybe an engineer is cranking up the temperature in the system. Well, that would in turn have an effect on the pressure. So in a related rates problem, we would want to know how are the rates of change of these variables related to one another. For example, if we know how fast the temperature is changing, could we determine how fast the pressure is changing? This is the sort of question that we want to answer today.
Hello once again. Today's topic is derivatives as rates of change and related rates. So before we get started, I want to remind you of some things that we talked about previously. The first of which is the idea of an average rate of change. So if you have a function f and you got an interval that starts at a and goes up to x, then this quantity f of x minus f of a over x minus a is the average rate of change of the function over that interval. We can also express that average rate of change in a slightly different way. And instead of going from a to x, we will go from x to x plus h. And then we can express it with this ratio here. But both of these things are doing the same thing. It's just measuring how much the function f changes over an interval and then dividing by the length of that interval. And then the idea was on either one of those average rates of change, if you make the length of the interval get shorter and shorter by taking a limit, the limiting value is what you call the instantaneous rate of change, and it's just the derivative. The instantaneous rate of change at the point x equals a is the derivative at a, which we originally defined as this limit, but we now know that we have ways to compute those limits without actually doing limits, right? We have things like the product rule and the chain rule and all these derivative rules that help us calculate instantaneous rates of change without doing limits. But one thing we see from either the definition of rate of change or the instantaneous rate of change is what it measures. When we look at those fractions, the numerator is measuring change in units of whatever f is measuring, and the denominator are units of x. And so the units of that fraction is units of f over units of x. So whenever f is measuring position in meters, then you get meters in the numerator, and if the denominator is measuring time, then you get time in the denominator. So maybe time was in seconds, so you'd get something like meters per second for your units of average rate of change. And the same thing happens in the instantaneous rate of change because you've got those same fractions in the numerator and denominator. So you get units of f over units of x here too for the units. Let's look at an example, a type of example that we've done before, and we'll add a little something new to it, the topic of velocity, speed, and acceleration. Remember from before that we can have a function s of t which measures position of an object traveling in a straight line. So usually this has some units like meters or feet. So we measure the positions along the line in how far they are from zero. And then the velocity you get as the first derivative. So in other words, velocity is the instantaneous rate of change in position. And something new that we'll introduce now, sometimes when we're talking about an object moving around, we want to differentiate what we mean by velocity versus what we mean by speed. Well, speed is just the absolute value of velocity. So whenever you look at the speedometer on your car, it's always a positive value, right? You might be going 60 miles per hour or whatever, but you're never going like some negative speed on your speedometer. So speed is just take the absolute value of velocity. Velocity, when an object is traveling in a straight line, keeps track of direction too, whether the object's moving in the positive direction or in the negative direction along that line. But speed doesn't care about direction. Speed just wants to know how fast the thing is changing. And acceleration, well, let's think about what acceleration ought to be for a moment. When you accelerate in your car, it means that you speed up, right? Like when you accelerate in your car, your speedometer goes from 20 miles per hour to 30 miles per hour to 40 miles per hour, that sort of thing. So what acceleration is doing is it's a measure of how fast the speed or the velocity is changing. So how do you keep track of how fast some quantity is changing? Well, you use the derivative, right? So what acceleration is actually the derivative of velocity. So a of t, except for acceleration, is just how fast the velocity is changing. But also, we already know velocity is the derivative of position, so we can think of acceleration as the second derivative of the position. So let's do an example to remind us how this works in practice. So I've got an example here where a rock is being dropped from a 100-meter high building starting at t equals 0 seconds. And then we have this position function, s of t equals negative 4.9 t squared plus 100. That keeps track of where this rock, which is falling in a straight line, is at, height-wise, at time t. So I can ask a variety of questions. Hey, at what time does this rock hit the ground? What's the rock's velocity and speed when it hits the ground? What's the rock's acceleration at time t? Well, let's just go through and work these out each one by one. Okay, starting with part A, at what time does the rock hit the ground? The ground would be height 0. So what this is really asking is, when is s of t equal to 0? So that's an equation that you can solve. So s of t is negative 4.9 t squared plus 100. You set that equal to 0. And from there, you can subtract 100 from both sides and divide both sides by negative 4.9. And you get t squared equals 100 over 4.9. And then if you solve for t, you'd get plus or minus the square root of 100 over 4.9. But, time doesn't run backwards in this example. Once you drop the rock, time moves forward. So we're going to disregard the negative root there for practical reasons. And I could write this as 10 over the square root of 49, or square root of 4.9 if I like. And so that's the time in seconds. And this is going to be, a little under 5 seconds if we punched it into a calculator. But I'm not going to bother punching it into a calculator right this second. Now, this answers the question, part A, at the time at which the rock hits the ground. So then I can use that to answer part B of what is the rock's velocity and speed when it hits the ground. So we know that velocity at any given time is the first derivative of the position function. And the derivative of that position function is, well, I differentiate negative 4.9 t squared. I bring the 2 down, so it'd become a negative 9.8 t. And then the derivative of 100 is 0, so you just get that. Now we can answer what the velocity is at the time when the rock hits the ground by taking the time when the rock hits the ground, which is 10 over the square root of 4.9, and plug it into the velocity function. And so that would be negative 9.8 times 10 over the square root of 4.9, which I will plug into a calculator. And it comes out to negative 44.27. And the units here, well, since the given information is in meters, and then time is in seconds, this will be meters per second. Now notice here that velocity is negative. That makes sense in this particular scenario because the rock is being dropped and it's moving downward. So it has a negative velocity to indicate the downward motion, up being positive. And then the speed is going to be the absolute value of v of 10 over the square root of 4.9, which would of course be 44.27. So speed is just always going to be positive because you're taking absolute value. So that's like the speedometer reading on the rock if the rock had a speedometer at the moment when it hits the ground. Part C wants to just know, what is the acceleration function? What is a of t? Well, a of t is the derivative of the velocity function. So that would be negative 9.8 times t prime, which is negative 9.8. So it comes out to be a constant. Now, what are the units here? Well, if you think about it, velocity is measuring meters per second, but then when we're doing the derivative again, we're doing with respect to t, so we divide by t again, or divide by time again. So this ends up being meters per second squared. And again here, this has a sign, negative, to indicate that the acceleration is sort of moving in the negative direction, in the downward direction. We can certainly look at other kinds of rates of change other than an object moving around and measuring its velocity and speed. For example, we could look at population growth, and we could think about how fast a population is growing. So in this specific example, I've got some bacteria in a culture, like in a petri dish or something like that. And after t hours, I have a function that approximates what the population is of bacteria at time t. Of course, we can't literally count the number of bacteria, so we have to have a function that tells us, the approximate count of bacteria. And there it is. And so I could ask a few questions related to average rates of change and instantaneous rates of change. The first question is asking, what's the average growth rate in the bacteria population over the first 100 hours? So when we talk about the first 100 hours here, what interval are we talking about? Well, if it's the first 100 hours, that'd be the interval from 0 to 100, right? So we want to do the average growth, the average change in the population, or the average rate of change in population over that interval. And then in the second problem, we want to do the instantaneous growth rate at a particular moment in time. So for part A, we would just do the population. So this average growth rate would be the population at the end of that interval minus the population at the beginning of the interval, all divided by the length of the interval. So P of 100, so you do 1,000 over 1 plus e to the negative 2. After you plug in 100 there, multiply times negative 0.02, you just get negative 2 for that exponent on e. Minus P of 0 would be 1,000 over 1 plus 1, and that's all divided by 100. Maybe to make it a little easier to plug into the calculator, I'll simplify it just a hair. So I could factor 1,000 out in the top, cancel with the 100 in the bottom, and I'd be left with 10 times. And I'm getting this comes out to approximately 3.8. Now what would be the units here? Well, this would be bacteria, is what the population was counting. And then time was being measured in hours. That seems awfully low, but that's what we got. And then the instantaneous rate is going to be part B. We want the instantaneous rate at time t equals 100. So that's going to be P prime evaluated at 100. So what is P prime? So first let me do P prime of t. Well, if I calculate that derivative, I think I'll use the quotient rule. So I take the derivative of the top, leave the bottom alone, but the derivative of the top is 0. So that term will end up being 0. Then I do minus, then I leave the top alone, and I multiply times the derivative of the denominator, which is going to be negative 0.02 times e to the negative 0.02 t, and then that's all over the denominator squared. So P prime of 100 will work out like this, and I'll punch that into my calculator and I find that this comes out to about 2.1. This would be in bacteria per hour. Okay, so the moral of the story here is that, we can do this, we can measure rates of change on all kinds of functions. Any function whatsoever, we can measure rate of change, either average rate of change or instantaneous rate of change, and then for whatever particular situation, we can make sense of what the units are, and we can interpret the results. In this particular case, we were just measuring how fast the population of bacteria were growing in this petri dish. The point of this next example is to point out that the variable doesn't always have to be time. When we were doing velocity, you're talking about change in position with respect to time. When we were measuring the population change, we were doing population change, changing over time. But we can interpret the results for other kinds of situations too. In this particular example, you got a boat. Maybe it broke down or something, and it's being pulled into the dock using a rope attached to a winch, as indicated in the picture there on the right. And in that diagram, I'm labeling the length of the rope from the winch to the boat by L for length. And theta is the angle of elevation going from the front of the boat up to the winch. Now clearly, as that boat gets pulled into shore, that angle theta starts to increase, right? It'll start to become close to 90 degrees as the boat gets close to the dock. And when the boat's far away, the angle will be small, close to zero. I want to know, how fast is that angle theta changing with respect to the length of the rope? What would that mean? So what we're really being asked to find here is, how fast is theta changing with respect to L? In other words, we're being asked to find, how fast is theta changing with respect to length, and then at the moment when L is equal to 50. Symbolically, that's what we're being asked to find. Well, from that picture, I need to find some relationship between theta and L so that I can calculate d theta dl. Well, what I see when I look at this diagram, I see a right triangle here. And in that right triangle, I think I might be able to relate theta and L. Notice that the vertical side of this triangle is 10 because that's the height of the winch. What trigonometric relationship would relate theta, 10, and L? Well, I can think of a few. For example, sine of theta, that's the opposite over the hypotenuse. That'd be 10 over L. Or I could do cosecant. That'd be L over 10. I think I may work with the cosecant formula. So we know cosecant theta equals L over 10. And from there, if I want to calculate d theta dl, I could do this a few different ways, but maybe the most direct way would just be to solve for theta. If I solve that equation for theta, I would get theta is equal to the cosecant inverse of L divided by 10. So then from there, I could calculate the derivative of theta with respect to L, because I've got theta expressed in terms of L, so it makes it easy to compute the derivative. Now, we learned recently that the derivative of cosecant inverse, let me remind you of the formula here. We had the formula written like this. The derivative with respect to x of cosecant inverse of x was negative 1 over absolute value of x times the square root of x squared minus 1, like so. So if we apply that formula to this situation, the L over 10 is going to be playing the role of x, and we just have to remember to use the chain rule. So we'll get negative 1 over absolute value of L over 10 times the square root. Then I'll have L squared over 100 minus 1. And then I got to remember to multiply times the derivative of the inside function. And the inside function is just L over 10, so if I multiply times the derivative of that, it's just the same as multiplying by 1/10. So I'll put that 1/10 here in the numerator. And I actually see that these 1/10ths here cancel. And also, I can drop those absolute values on L because L is the length of a chain, which I know is positive. So this just ends up being negative 1 over, let's see, then I got L. And inside that radical, I could get a common denominator and write it like L squared minus 100 over 100. I could take the square root of that 100 in the denominator, and I'd have a L over 10 in the denominator, which I can bring that 10 up to the top, so I end up with negative 10 over L square root of L squared minus 100. Maybe that's a nice way to write it. Okay. So if that is my derivative of theta with respect to L, how do I answer the question? Well, I need to find that derivative when L is equal to 50. So now I can just plug 50 in for L. So d theta dl when L is equal to 50 is negative 10 over 50. And then inside that radical, 50 squared is 2,500. So you'd have 2,500 minus 100 would be 2,400. And I could write that as, so I'd have 5 times 20 squared is 6 in the bottom. So you get some strange number. So 5 times 20, I'll make that 100. So I think it works out like that if I did my arithmetic correctly. And what are the units here? Well, theta was measuring things in radians because it's an angle. And anytime, since we differentiated the way we did using our standard differentiation formulas, we were assuming everything was in radians. And then L was being measured in meters. So this is radians per meter. So what does that mean? So the second part of this was to interpret this solution. This one's a little weird to interpret, but if we just think about the units for a second, if it's measuring radians per meter, this means that something like for every meter that the length of the rope lengthens, the angle decreases by that amount, negative 1 over 100 squared of 6. So the interpretation here is for every meter that the rope lengthens near L equals 50 meters, the angle changes by negative 1 over 100 squared to 6 radians. Or in this problem, it said that the boat was being pulled into the dock. Well, that tells me that the rope is shortening, right? So I could interpret this sort of inversely, or for every meter the rope shortens near, so this time I'm going to make the rate, I'm sort of putting the negative into the denominator of the derivative. For every meter that the rope shortens near L equals 50, the angle increases by 1 over 100 squared to 6 radians. That more matches our situation here, right? As the boat's being pulled in, that angle gets bigger and bigger, closer to 90 degrees. So I think this is the interpretation that we were looking for here for that derivative. All right, so with these examples of understanding that the derivative is giving instantaneous rate of change and that you can look at the units associated with that and give it some interpretation, let's start talking about related rates. So related rates problems have some identifying characteristics. The first of which is that you usually have several variables that are related. So maybe your variables are x, y, and z. Could be 2 variables, could be 3 variables. Heck, could be 10 variables. Typically, you don't see more than, say, 3 or so in the problems that you'll be seeing. But in the real world, there could be hundreds of variables. And then those variables are related to each other by some sort of equation. Or maybe there's a few different equations that you can use to relate them. But for example, maybe you have something like x squared plus y squared equals z squared or something like that going on. And when we're talking about these kind of related rates problems, typically each variable is changing in time. So we're going to go back to that situation where t is our variable that everything is changing with respect to. And so that means that each of the variables that are in play, you can think about their derivative with respect to t. If they're changing in time, then we can measure that rate of change in time. So things like dx dt, dy dt, dz dt, if those were our three variables, x, y, and z, these three derivatives make sense. We can give some interpretation to them. And then typically you're given some information about some of the rates of change. So maybe you're being told something like, hey, dx dt at some moment, maybe like when t is equal to 5, is equal to 3, and dy dt at that moment is equal to 4. Maybe you're given some information like that. Now, you may not be given all the information about the rates of change of all the variables, but some of them. And then the goal will be to find the rate of change in one of the variables that you're curious about using the supplied information. So we might be trying to figure out, like, what is dz dt at the moment when t is equal to 5. It's hard to talk about this too much in the abstract, so what we need to do is just start doing some examples and you can see what I'm talking about. So let's start with a fairly straightforward example. We've got a spherical balloon. Now I know that real-world balloons aren't typically perfect spheres, but to make life easy on ourselves mathematically, we're going to assume that our balloon is perfectly spherical and it's being inflated at a particular rate, 100 cubic centimeters per minute. So we got some air compressor pumping air into this thing at a steady rate. Now as the balloon's inflating, it's getting bigger and bigger, right? So it would make sense to ask, how fast is that balloon's radius increasing at a moment in time, say when the radius is 20 centimeters? So in these type of problems, almost always your first step is going to be to draw a picture of what's going on here and then label that picture with some variables. So I'm going to do that here over to the side somewhere. So I've got this balloon, and that's a sphere. That sphere is changing, like it's growing, right? It's got this radius, but the balloon itself is sort of getting bigger and bigger. So the radius isn't some fixed value. The radius is just, let's just call it r. So r is a variable. And then, what do we know about the volume of a sphere? Well, you may not remember, but the volume of a sphere actually turns out to be 4/3 times pi times the radius cubed. Okay, so I've described my situation there, and I think I have all the pertinent variables sort of down. I've got v is volume, r is the radius. Now, what's this thing asking me about in terms of in these variables? And what am I given? So it's usually a good idea to write down what you're given in the problem. The main bit of information I'm given is that the balloon is being inflated at a certain rate. Well, notice that rate, 100 cubic centimeters per minute, the numerator there is volume, and the denominator is time. So you can tell from the units being given that what I'm being told is what the derivative of the volume is with respect to time. I'm being told that dv dt is a nice steady 100. Now, what are we supposed to find in this problem? What are we being asked to solve? Well, I'm wanting to know how fast the balloon's radius is increasing at a particular moment. Well, we named the radius r in our picture over there, so we want to know how fast r is changing with respect to time, but at a particular moment. So we usually put that bar to indicate derivative at a point, at the point when r is equal to 20. So now we've got two variables, v and r, that are related by this equation, v equals 4/3 pi r cubed. You can see why these are called related rates, because there's a relationship between them, and then you can use that relationship between those variables to establish a relationship between their rates of change. So given that we know v is equal to 4/3 pi r cubed, from there we can differentiate both sides of that equation with respect to t. On the left-hand side there, that's just dv dt. On the right-hand side, I'm going to differentiate that expression, but I do want you to see something here. The variable that we're differentiating with respect to is t, but the variable that's present in the expression is r. But we understand that r is a quantity that's changing in time. The radius is increasing over time as that. So you should be thinking of that as r of t, like some sort of function. So when you differentiate it, you got to give it the respect that a function deserves and use the chain rule. So that's a whole function cubed, and to differentiate it, I would bring the 3 down, and it would cancel the 3 that's in the denominator there, so I'd have 4 pi r squared, but then r is a function, so I have to multiply times its derivative, dr dt. Now that's great because the thing that I'm trying to find, dr dt, is right there in my equation. So I think because I'm trying to solve for dr dt, I'll solve for drt in this equation. And also notice that we can replace dv dt in this equation by 10 because we were given dv dt. I'm sorry, it should be 100. We were given dv dt equals 100. And now I can solve for dr dt, and it would be 100 divided by 4 pi r squared, which I'm going to simplify just a hair. 4 goes into 100 25 times, so I'd have 25 over pi r squared. And now I'm ready to get the final answer because I wanted to find out what dr dt was at the moment when r was equal to, what was it? 20. So that just means put r equals 20 into the derivative there. So 25 over pi times 400 is what you get when you square 20. And I suppose 25 we can do a little simplification here and get 1 in the top and 16 pi in the bottom. And what are the units here? Well, r was being measured in what units in this problem? Centimeters. So the units on this would be centimeters, and then since we're differentiating with respect to time, we have to look and see what were the units of time in the problem. It was minutes. So this is centimeters per minute. You can kind of look at what I did here and sort of make some steps out of it. The first thing I did was to draw a picture, write down an equation. Well, I drew a picture and I labeled the variables that were in play on that picture. I wrote down an equation that related those variables that were inspired by the diagram, and then on the right I wrote down what it is that I was given and what I needed to find. That's a good way to get these problems started every time. You can write down these steps, which is good to, maybe if you ever get stuck on one of these problems, you want to kind of go back to this and make sure that you're doing all these things. Of course, read the problem carefully, draw a picture, identify the rates that are given and the rates that are to be determined. So that's when I wrote given and find a minute ago. Write down one or more equations that express basic relationships among the variables. Then you differentiate the appropriate equation with respect to t, like we did. And then you substitute known values and solve for the desired quantity. So remember when we substituted 100 in for dv dt, and then at some point we put in r equals 20. And then at the end you kind of look at your answer and go, does that make sense? Let's have a look here at another problem. So in this make pretend problem, 2 cars are taking off from the same point and at the same time. Car A goes south at 60 miles per hour and car B heads east at 80 miles per hour. Then I want to find out how fast is the actual straight line distance between the cars increasing 15 minutes after they depart. So let's draw a little picture of what's going on here. So here's the point where they depart, and I have one car that's headed east at 80 miles per hour and one car that's going south. Okay, car B goes east. Car A goes south. And B was going 80 miles per hour. Car A was going 60 miles per hour. The distance that each of these cars travels in a straight line is variable, right? So maybe I called, the distance that each car has traveled at a given time, x and y. So x and y here are functions of t. And then what I'm looking to do is measure something about their straight line distance between them, like how far is the distance between those 2 cars increasing. Maybe I'll call that distance z. And note that since one car's going south and one car's going east, that the angle between their directions is a right angle. Well, you look at that figure and you start thinking, man, is there some way that I can relate those variables? Is there some common formula that relates the sides of a right triangle? Maybe. Like perhaps when I see a right triangle, one of two things pops to my mind. Pythagorean theorem, or if any angles are known besides the right angle there, maybe I would use a trig function. But I don't really know anything about any of the other angles, so I think just observing that x squared plus y squared is z squared here is probably the relationship that I want to observe among those variables. And of course, one of the first steps is to write down what it is you want to find in terms of derivatives. Well, let's write down what we're given. What was it that we were given in terms of rates of change? Well, the 80 miles per hour and the 60 miles per hour are telling you how fast those distances x and y are changing. So I see that dx dt is a steady 80 miles per hour, and dy dt is a steady 60 at any given time. And then what we want to find is how fast that distance between the two cars is changing. So we want to find dz dt, and we want to find it at the moment when t is equal to 15 minutes. Now we have to be careful with units here because those given speeds were in miles per hour, not miles per minute. So maybe it would make sense to, instead of say we're wanting to find what happens at t equals 15 minutes, to replace that with t equals 1/4 of an hour. Okay, so you got to be careful about units in these problems. It can really throw your answer off if you get mixed matched units. So we know what we are given, and we know what we need to find. So all those rates that we're looking at, the givens and the find, we have to relate those rates to each other using whatever equation that we have that relates the variables. So in this particular problem, I think what I'm going to do is start from x squared plus y squared equals z squared. I'm going to differentiate both sides with respect to t. So I'm doing implicit differentiation here. Now you have to understand that each of those variables, x, y, and z, they're all functions of t because they're all quantities that are changing in time. And so I have to treat them with the respect that a function deserves when you differentiate it. So calculating those derivatives, that first derivative there would be 2x times dx dt plus 2y times dy dt because y is a function of t. And then on the right hand side I'll get 2z times dz dt. I can make some simplifications here and also use some of the given information that I have. For one thing, we know that dx dt is 80 and we know dy dt is 60. And also you could divide both sides of the equation by 2 and just get rid of those 2's. So after substituting what we know and canceling some things off, this simplifies down to 80x plus 60y equals z times dz dt. And I want to go ahead and solve for dz dt because that's what I'm trying to find at the top left there. That's what I'm looking for, right, is dz dt. Now I want to find dz dt at the moment when t equals 1/4, but let me just find dz dt at any given t first, and then we'll think about how to plug in t equals 1/4. So dz dt, if I solve for it algebraically in the last equation, I get 80x plus 60y all divided by z. Okay, so now that we get to the question of how do you do dz dt at the moment when t equals 1/4. Well, that presents me with a little bit of a difficulty because when I look at this expression here, I don't see any t's to plug in for. Well, what we can do though is go back to the original picture and think about what's happening at that particular time. So in our original picture here, maybe I'll just make a copy of it here. Well, we know that first car was going 80 miles per hour, right? One going to the east. But if you drive 80 miles per hour for 1/4 of an hour, how far will you have gone? Well, you'll have gone 1/4 times 80, right? So this distance would be 80 times 1/4 at that particular moment in time, so 20. And likewise, on the other side, that car was going 60 miles per hour. So you do 60 times a quarter, and that'd be 15, right? In our little triangle picture, at that particular moment in time, the horizontal side was 20 and the vertical side was 15. And we can also then figure out what that hypotenuse was at that particular moment in time, because now we know two sides of that triangle. The side that's 15 now was our y, and the side that was 20 was our x. And so we have this z here. We know z squared equals x squared plus y squared. In other words, z squared at that particular moment, at t equals 15, well, 1/4 of an hour, z squared is equal to 20 squared plus 15 squared. So z squared equals 400 plus 225, so 625. I think that works out nicely because you can take the square root of that and z would be 25. Excellent. So at that particular moment in time, we have all three of our little quantities there known. We got z is 25, we got x is 20, and we got y is 15. So now we can substitute that information in to our derivative formula. So this ends up being 80, and then at that moment x was 15. I'm sorry, x was 20. X was 20, and then we had 60 times our y, which was 15, all divided by our z, which was 25. And that works out to be 100. And then the units are, since z was being measuring miles and time was being measured in hours, we end up with exactly 100 miles per hour. And that's our answer. And when I think about how fast those cars are going away from each other, that kind of makes sense. I mean, they're not driving directly apart from one another. If they were driving directly apart, like one was going east and one was going west, then it would just be the sum of their velocities, right? But here it's going to be somewhere in the middle, not all the way 140 miles per hour. Yeah, answer seems reasonable to me, so I think we're good. In these diagrams, you usually find some sort of geometric relationship, like a Pythagorean theorem, or sometimes there's just a volume formula that you know, these sort of things. So let's try another one. Really, just practice makes perfect on these things. These problems are not easy, though, because there's always a lot going on. Not only do you have to know your calculus and get familiar with like seeing derivatives when they like interpreting what are derivatives in the problem, you also have to draw on previous experience, geometric relationships that you're supposed to know, and things like that. In this example, we have a person who sees an airplane fly overhead, and they can tell that airplane is flying due east, and it turns out that the airplane is at an altitude of 3 miles and is flying with a speed of 500 miles per hour. Now, as a person would see an airplane flying off into the distance, that person could measure the angle of elevation from them up to the plane. And as that airplane flies into the distance, that angle of elevation is going to change. In fact, it's going to get closer and closer to zero as the plane flies off to the horizon. So the question is, how fast is the angle of elevation from the observer to the plane changing at the moment when the plane is 4 miles due east of the observer? So we've really got to draw a picture here, get our heads around what's going on. So let me draw my little observer here. Little stick man, it's the observer. And overhead, there's this plane that's flying due east. Here's my plane. I know it's a work of art. And that plane has a speed of 500 miles per hour. And that angle of elevation that we're talking about in this problem is when you draw a line from that person to the airplane, and then you look at the angle from that line from the person to the airplane, that angle that line makes with the ground, with the level ground. Let's call that angle theta. That's your angle of elevation. Now, it was stated in the problem that the distance between, the airplane was flying at a height of 3 miles. So I'm starting to see a right triangle appear in this problem. And also, I remember from geometry class, the line that this plane is flying along on this horizontal is parallel to the ground. And then remember these alternate interior angles? So this angle up here by the airplane is also theta. Those two angles are equal. We know something about how far the plane is away from the person horizontally. We know at some point they're 4 miles away horizontally. So maybe I'll label that top variable with x, because I have some information like x is going to be equal to 4 at some point in time where I'm going to be interested in. And also, since I know the speed of the airplane, I can figure out what x is at any given time. X is just going to be 500 times t. So what would be a relationship sort of relating theta to the variable and things that we know in this picture? Well, I see a tangent there. I see tangent of theta equals 3 over x. Or maybe I could even write it a little nicer if I express that as x equals 3 times cotangent theta. Yeah, I think this might be the relationship that we want here. X equals 3 cotangent theta. I could have worked with tangent of theta equals 3 over x, but because of the fraction, I think it would make it a little harder to work with. So what we're given in this problem, in terms of the variables that I have here, I'm given that dx dt, that's the speed of the airplane, is 500. Steady 500. And it looks like what I'm being asked to find, in terms of the variables in play, is I want to know how fast that angle theta is changing at the moment when x is equal to 4. Let's see if we can get something going here. Since we know x is equal to 3 times cotangent theta, then I can differentiate both sides of that with respect to t. I just have to remember that all the variables are functions of t, and treat them that way. On the left-hand side, the derivative of x with respect to t is just dx dt. And on the right-hand side, I remember that the derivative of cotangent is negative cosecant times cotangent. So this will be negative 3 cosecant theta, cotangent theta. But then I got to remember theta is a whole function of t, so that's times d theta dt. So I know dx dt is a steady 500, so I know at this point, and that's regardless of what particular time we're talking about, so I know I can just set that equal to 500 right there. And so from there, I can see that d theta dt, I'm going to divide both sides by negative 3, and then I'm going to multiply both sides by sine of theta to get rid of the cosecant. I'm going to multiply both sides by tangent to get rid of the cotangent. So I'm just multiplying by the reciprocals of things to make it look nice. And now how do I find d theta dt when x is equal to 4? Well, kind of like that last problem, I got to figure out what theta is equal to whenever x is equal to 4. But I can look at a copy of my triangle here that we're playing with, and we're at a situation where, like, the vertical side here I know is a steady 3, and we're doing the moment when x is equal to 4 on the top. So I see that this is a 3, 4, 5 triangle. If I use the Pythagorean theorem, the hypotenuse there is 5. And that angle up there in the upper right-hand corner is the one we were calling theta. So you can just read off from that triangle now, what is sine of theta? Well, sine of theta is the opposite over the hypotenuse. That'd be 3/5. And the tangent is the opposite over the adjacent, so that'd be 3/4. So now this is all happening at, when x is equal to 4, right? So we get negative 500 over 3. The sine of theta worked out to be 3/5. And tangent of theta worked out to be 3/4. And, I can do some simplifications here. Looks like it works out to be negative 75. And then the units here, we're measuring theta, which is measured in radians. And the time was being measured in hours because the units were in miles per hour. That sounds like a big number, but that's how much an angle changes over an hour. So if you sort of thought about it on a per second basis, it's not spinning that fast because there's 3,600 seconds in an hour, right? So anyway, that answer seems reasonable to me. And even the negative makes sense because as the plane flies away, this angle is going to be turning in a clockwise way, like the angle is going to be decreased. And we know that when we measure angles counterclockwise, it's the negative direction of rotation. So the negative just means it's counterclockwise. So this is part of that last step of, does my answer make sense? So think about the sign of it and think about the magnitude of it, and just does it make sense? Sometimes it's not easy to tell if it makes sense if you don't have a lot of intuition about, the particular scenario that you're dealing with. So that part can be tricky, but with more experience, you get better at that sort of thing. Okay, here's one last example. In this example, we got this cone-shaped tank, and it's inverted, so that means that the point of the tank, the point of the cone's going downward. And it's got water in it. The tank has a height of 10 meters and a radius of 5 meters, and the water's draining out in the hole in the bottom. And we got a specific rate at which the water is draining out. It's draining out at 3 cubic meters per minute. So the question is, how fast is the depth of the water changing at that moment when the depth is 6 meters? So let's try to get a picture of this going. I know the radius of the cone, that just means the radius of the circle at the very top of it is 5. And I know the height of this thing, so measured from the center of the top circle down to the point, that's 10 meters. And then it's draining water, so there's a water level inside here. Maybe I'll just indicate that with a blue circle here. So this right here is the water level. Now the water level is changing because the water is draining. So if I would look at the radius of the water level, that would be variable. Let me put that as an R there. And also the height of the water level, I'll call H. That's changing in time. So R and H are both quantities that are changing as the water drains. Whereas the 5 and the 10 measurements for the whole tank, those are fixed. Now, one thing you may or may not know about a cone is that a cone, there's a volume formula for it. The volume of a cone turns out to be 1/3 pi times the radius of it squared times the height. When I think about what I'm being asked to do and what I'm given in this problem, what was I given? What kind of stuff? I circled something in red there, felt like it was important. I know how fast the water is draining out. So if I know how fast something is changing, that's telling me about a derivative. And I can look at the units to tell me, what it is that's changing. Well, meters cubed is a volume measurement per minute. That's time. So what I can see is going on here is that the volume with respect to time, that rate is 3, but the water's draining out, so I think the volume's becoming less, so I'm going to make that a -3. And what I'm being asked to find, it says how fast is the depth of water in the tank changing? Well, the depth of water in the tank on my picture was H. So what they're asking me to find is what is dH dt, but then not just how fast is the height, the depth of the water changing, but at a particular moment when the depth is equal to 6. So I have one derivative on V that I'm given, and I'm wanting to find a derivative on H. So that means I need a relationship between V and H. Well, in my volume formula here, I kind of have a relationship between V and H, but there's a third variable in there, R, and I don't see anywhere in the problem anything about how fast R is changing or So when I get in a situation like this where my equation has more variables than I have information in the problem, it means I probably need to look for another relationship between variables. And in this particular problem, there is a secondary relationship that we can observe. Look at this triangle right here in yellow, and then compare that to the triangle that I'm going to shade in red here. Notice that both of those triangles have a right angle, and they share the angle at the bottom. And they also, so anytime you have two triangles that have two equal angles, they're what are called similar triangles. And similar triangles have the lengths of their sides are in proportion to one another. So if I would look at, say, R over H in the small triangle shaded red, that would have to be the same as the corresponding sides on the big yellow triangle, which would be 5 and 10. So that tells me that R, I can solve for R in terms of H, and I could say R is equal to H over 2. So there's a secondary relationship. In this particular situation, R is always H over 2, so I could actually just substitute H over 2 in place of R here. So with that in mind, so we have v is 1/3 pi, and then h over 2 squared times h. And let me simplify that down to, well, I'll have a 1/4 times a 1/3, so I'll have 1/12 pi, and then h cubed. Now I can talk about taking the derivative of both sides of this with respect to t, which have to remember that all the variables v and h, they're functions of time. So on the left-hand side, the derivative of v with respect to t is just dv dt. And on the right-hand side, I'll bring the 3 down, so I get 1/4 pi h squared. But then h is a function, so I have to multiply times dh dt. And now if you look at what we're trying to find up there, we're trying to find dh dt at the moment when h is equal to 6. And also, we were given that dv dt is always -3, so I could go ahead and substitute here -3. And so when I solve for dh dt, I'm going to get -12, so multiply both sides by 4, and then divide both sides by pi h squared. That's dh dt. So from there, I can find out what dh dt is at the moment when h is equal to 6. I would just plug 6 into that previous expression, and I'd get -12 over pi times 36, or simplifying, -1 over 3 pi. And what are the units? Well, the lengths in this problem were being measured in meters, and time was being measured in minutes, so this would be meters per minute. I'm happy that my dh dt was negative, because in that, as the water is draining, the depth of water is decreasing, right? So the negative indicates that we have a decreasing depth of water. So that passes some sort of sanity check. If I had gotten a positive answer, I would know I screwed up somewhere. And then the number of 1 over pi thirds meters per minute. I mean, I think the tank is draining kind of slowly. It's a very large tank if you paid attention to the measurements of it. It's 10 meters tall by, I mean, imagine a 10 meter tall tank, right? That's like, over 30 feet tall. So it's a giant tank, but it's only losing 3 cubic meters of water every minute. So, I mean, that's a lot of water. 3 cubic meters, it's a giant trough full of water, but this is a big tank, so the water is not going to be dropping super fast. So I think the answer makes some sense. So while it's possible I made some calculation mistake along the way, I feel good about it. So short of double checking my work, I think I'll stop there. Okay. Well, as you start trying to do these problems, you will undoubtedly get stuck somewhat, and you'll find that these problems go a lot slower than the other kind of problems that we've done so far. So you'll want to give yourself plenty of time to do these, and allow yourself to draw a picture and scribble around, and use a lot of scratch paper to sort of get ideas down. But if you'll follow this template of drawing a picture, identifying any relationships between the variables involved in the picture that you can, stating what you're given, and stating what you got to find, that really helps guide what you need to do next. Okay, we'll stop there. I'll talk to you again soon. Bye now.